Welcome back, students. Let's resume. We did some power functions, exponential functions. Now let's move on to trigonometric functions. Here are the antiderivative rules for trigonometric functions. And again, here I'm using the extended form ax plus b inside each. And then please note the recurring theme of 1 over a. Every single time we have 1 over a, we discuss why that is the case. Oops. Derivative of sine is cosine, so antiderivative of cosine is sine. Derivative of cosine is negative sine, so antiderivative of sine is negative cosine. These two can get rather confusing, so please be careful about pluses and minuses. And then a couple more. Derivative of tangent is secant squared, and derivative of cotangent is negative cosecant squared. And we have the other way around. Well, again, it can get a little bit confusing, you see. A little bit more. Derivative of secant is secant tangent, so antiderivative we go backward. Derivative of cosecant is negative cosecant cotangent, so we go backward. Again, pluses and minuses. They can be confusing, so be careful about these. Let's see, shall we go ahead with some computation problem? Okay, here we go. Let's calculate this antiderivative. Okay, what's the antiderivative of 1? Just u, isn't it? Good. What's the antiderivative of cosine? It should be sine. But that's not the end of the story. I need 1 over a. Minus. How about the exponential part? Exponentials stay the same, but I need 1 over a. If you just remember 1 over a, you can do all these. No problem there. Do I have that in my answer key here? Yes. No problem there then. How about something like this one? This is going to be a bit harder because it looks like we have a multiplication. But how did he handle those kind of thing in power functions? What did he used to do? We used to break up the parentheses, right? That's what we're going to do. Distribute around, then you're going to get secant squared. And then this is going to become secant tangent. Alright, what's the antiderivative of secant squared? It's tangent. What's the antiderivative of secant times tangent? It is secant. So what do you get? Tangent of t, oops, tangent of t minus 2 secant of t. Here's the answer key. Well, if you don't know the antiderivative formulas, you can't really do too much, so it's important you keep these handy. Better yet, memorize them. How about a problem like this? Please remind yourself, what did he do for fractions? There's no such thing as quotient rule for antiderivative computations, so we did something special, something different. How did he do things differently? We separated the numerators and then simplified each, right? Okay, how do we simplify? 3 over sine squared. Is there any good way to simplify this thing? Oh, by the way, while you guys are thinking, looks like I may have to go several steps, so let's move it to the next line. 3 over sine squared. Any good way to simplify? 3 cosecant squared. This one is easier. Sine squared over sine squared, so that's just 1, so just plus 4. And does it help? Yes, it does. What's the antiderivative of cosecant squared? Oh, I forgot coefficient 3. Antiderivative of 4. And there goes the answer. Again, you gotta remember these rules here. Antiderivative of cosecant squared, I just used that one. We have this negative cotangent of v. Pluses and minuses can be confusing. So if you can't rememorize all these really accurately, and you can get, okay, sine becomes cosine, cosine becomes sine, and pluses or minuses look up. Secant squared, cosecant squared, tangent, cotangent, but the detail look up. Secant, tangent, cosecant, cotangent, we have secant and cosecant, but detail look up. Maybe that's a good idea, because if you do not at least partly memorize, then the idea to simplify this 3 sine over sine squared into 3 cosecant squared, or better yet, whether this is separation of this numerator, that idea may not come to you. So if possible, memorize these formulae. If not, at least you remember the overall structure. You may be missing some pluses and minuses and things like those, but overall structure you should at least get used to. Now, these kind of problems are a little bit different. Squared cases. How do we handle trig integrals when trig functions are squared? We have to use appropriate trigonometric identity for that. And if you can memorize this formula and just use it, that's fine. And I'm not going to scrutinize that really. In Calculus 2 I will, but in Calc 1 I won't. But assuming the students who are in this video are looking at Calc 2 in the future, let me tell you how to work it out. Sine squared is 1 minus cosine of 2x over 2. It's one of the half angle formula or power reduction formula, whatever you want to call. And cosine squared is 1 plus cosine of 2x. After that, we simply take the antiderivative term by term. Let's see, 1/2 becomes 1/2 x. And then cosine of 2x sine, and then we need extra 1/2. So this is, you see, 1/2 which was there before, times another 1/2 because of this 1 over a. And that's how you get 1/4. So this derivation is going to be important for Calculus 2, but in Calc 1, if you just remember these and then just use these as formulae, I wouldn't mind. How about tangent squared and cotangent squared? Again, in Calculus 2, I want derivation, but in Calc 1, if you just use these as formulae, that's going to be fine. In Calculus 2, what should you do? You have to use Pythagorean identity. Tangent squared is secant squared minus 1, and antiderivative of secant squared is tangent. And the antiderivative of 1 is just x, so here's the formula. How about cotangent squared? Again, it's Pythagorean identity. Cosecant squared minus 1, and then you go from there. remember the derivations if you're going to go over to Calc 2, or maybe you can delay it and learn it again in Calc 2, whatever you may want to. But here for these problems, either you look up or go ahead with derivation. Here they are. These are Calculus 2 style answers. One more? Okay, again, this belongs more to Calculus 2. Yes, I have written this kind of problems in Calc 1 as well, but it's closer to Calc 2 problem. This is related to inverse trigonometric function. What? Inverse trig? Well, in Calc 2 they show up. Let's see. No, these are not very good. Let me show you the derivative formula for inverse trigonometric functions. Arc sine of x is derivative of arc sine is 1 over square root of 1 minus x squared. This one, we don't use it very often. Arctangent of x, derivative of arctangent is 1 plus x squared. This one is far more important for antiderivative computation. And this is what we use over here. How do we do that? Okay, here we go. Use complete square. Complete square plus 1, so we get this thing squared plus 1 like that. And then we apply antiderivative formula for arctangent. So what do we end up with? Arctangent of x plus 1 plus some constant c, of course. Too difficult? Yeah, I guess so. In Calculus 2 this is standard, but in Calculus 1 it's difficult. As a matter of fact, all the tricks and inverse trig problems are kind of borderline, sitting between Calc 1 and Calc 2. First three problems definitely are within Calc 1, but D, E, F, those are in borderline. So what do? Most of the time I do not write these kind of problems, but sometimes I do pick those up as A-level problem in Calculus 1. In Calc 2, those are standard problem. Even C students should be able to handle these kind of problems, but in Calc 1, those are A-level problems. So I sometimes do that. Not all the time. These kind of problems, of course, those are all standard. Just remember the antiderivative function and then 1 over a, the recurring theme of 1 over a. This kind of thing, break up the parentheses and then antiderivative formula for each term. Just look up, or better yet, memorize the formula. A little bit harder this time because you have to separate the numerator and simplify, but the simplification, the second term, was straightforward. But the first one, cosecant squared, and you're simplifying like that because you're anticipating the antiderivative of negative cotangents in advance. So it's a little bit higher level, but that's something definitely you can under. Okay, so much for trigonometric functions for this. And we're going to talk about another aspect of antiderivative problems in the next video.